In this question, we're asked to find the electric field of a long charged wire. Basically, here is this charged wire here. As we can see, it is positively charged. We're told that it has a length of L. So from here to here, the length is L. And also it has a linear charge density of lambda. So in order to do this question, we can do it with we can do it with a messy integral mathematical sort of way. But then we can do an even simpler method using Gauss's law. Basically, with Gauss's law, Gauss's law helps us to find the electric. It will help us to find the electric field due to this long charged wire. The first thing we do is to construct a Gaussian surface along the wire. So the most appropriate Gaussian surface we can create here would be a cylinder. So let me just go to question like that. As you can see, we have drawn this Gaussian surface in. So now our duty is to find the electric field. But then there is a formula which relates the electric field. That is the Gauss's law. And the formula goes like this. It says that the net flux is equal to the integral of the electric field, which is a vector, times the area, but then this is also equal to Q inside of the Gaussian surface divided by E naught. So this is still the same. This is Gauss's law. So we're going to use Gauss's law in order to find the electric field along a long charged wire. So let's go through it. The piece of information they gave us is that it has a linear charge density of lambda. So it has a linear charge density of lambda, and we are given the length. So already you can see that the Q inside will be equal to the linear charge density multiplied by the length, because the linear charge density is the charge divided by the length. So this length will cancel out with this length, and then we're left with only the charge. So Q inside will be equal to the linear charge density multiplied by the length. Now let's look at another thing we can look at is the net flux inside, net flux in the Gaussian surface. So let's start constructing our areas around the Gaussian surface and see what happens, what is the pattern. So if we take out an area here, we're going to have a dA, which is the area, the derivative, the integral of the area, so many areas. So in reality this is very small. Then what we have also is an electric field coming out here, going like this. These are all vectors. Okay, and an interesting thing with that we see is that the electric field is parallel to the area. So let's pick another place. Let's pick this point, this part here. Still here we have the area, then still we have the electric field coming out. Still showing the same pattern here, whereby the dA here is parallel to the E. Okay, let's do another point now, which will be very interesting, the side here. When you come into the side, things start to become interesting, because what you see here is that the area goes this way, so this is a dA, but the electric field is going up like this. So already here we can see that something interesting is happening. The area vector is perpendicular to the electric field, so they are forming a 90, and we know that in order to find the charge here, we're going to have a cos of 90 here, because the angle is no longer 0. When here the angle here is 0, so cos of 0 is 1, but then the angle here it's 90, and cos of 90 is 0. An interesting thing will also happen this side. If we took this as the top and this one as the bottom, this one will be the wall. So we can see that the net flux at the top will be equal to 0, and the flux at the bottom will also be equal to 0. So in reality, what contributes to the net flux will be the wall, what is wrapping around. So let's write something down. So the net flux E will be equal to the flux at the top plus the flux at the bottom plus the flux at the wall. So already we know that this one goes to 0, and also the flux at the bottom is also equal to 0. So what really happens is that QE will be equal to it's not QE, sorry. The net flux will be equal to the flux at the wall. So we know that the flux, the net flux will be equal to the flux at the wall. But then what is this flux at the wall? Can we further simplify this? Yes, we can do that. Since if you focus here, if we focus here, we can see that since the direction, since the area vector and the electric field are parallel to each other, this means that we can easily remove E out of the integral sign. So let me just do something for my, so it's sorry. Since we know that it's E times dA, we can remove this dot here, since both of them are parallel to each other. So we can remove this dot here, and we'll get something like this. We know that the electric field remains constant, so we can take it out of the integral sign. By the way, since you see that this is an integral, but then it has this round means that this integral is definite. And then we have dA here. So the dA here is actually the surface area of the the cylinder. So we can further write this as times 2 pi, then we have r multiplied by the length here. So we have our QE. This is our QE. It's E times 2 pi RL. The R here, it's the radius from the center to here. It's R. We're basically done now. We're almost done. So we have to just put everything together. So let's put everything together. Let me change color for the sake of doing it. The net electric flux is equal to 2 pi R L E, but then this is equal to Q in over E naught, and still this can further be simplified as lambda L divided by E naught. If you can, this we found here. So we found that Q in is lambda, the linear charge density times the length. So here, and we found that the net flux is equal to this. So put it here. So what's left now is just to make E the electric field subject to the formula, and you can easily do that as E wire will be equal to 2, will be equal to, we divide here, lambda divided by 2 pi E naught multiplied by the radius. So this is our final answer. The electric field due to a long wire is equal to the linear charge density divided by 2 pi E naught multiplied by the radius of that cylinder. And you could do the same question using a complex derivation, but then this is really enough for you. Thank you.